Right! Get out, you alcoholic! Out! Out, 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 out!
I haven't been drinking!
Are you stealing Dennis cars to support your alcohol?
That's my car!
Legions of machines made in our own image. Metal men to do our bidding.
Hello, Kismet. You gonna talk to me?
For scientists, the reality of that dream is much harder to achieve. But there are pioneers who relish the enormous challenge of integrating mind and machine.
Okay.
Go? No, I'm not gonna go. Yeah.
When it comes to their intelligence, today's robots are in their infancy. But, like human babies, they are learning. The vision is for robots to help in all areas of our lives. With the elderly, in our homes, in our hospitals, even on the battlefield.
Robotics has become hot. In the last half dozen years, we've gone from no robots in ordinary people's homes to millions. And this is just the start.
If we are soon to share our lives with robots, Australian-born Professor Rodney Brooks is determined to have something to do with it. He made both his career and his fortune creating simple, smart machines. Now, Rodney Brooks believes that a complex, socially aware robot is finally within his grasp, and our checkbooks. Welcome to Rodney's brand new world of robots.
We seem to be made to suffer. It's our lot in life.
If you've been to the movies any time in the last 50 years, you could be forgiven for thinking we would have had building robots all figured out by now.
Hollywood makes it seem like it's just easy to build robots that are as smart as humans. Sometimes even a lightning strike will make it happen. But in fact, to get anything that a human can do physically in the world is really, really hard.
Don't get technical with me. You'll be malfunctioning within a day, you nearsighted scrap pile.
Professor Brooks has been building robots for 24 years at the Massachusetts Institute of Technology in Boston. His base is here at the futuristic Computer Science and Artificial Intelligence Lab, Center of Cutting-Edge Robot Design. Last year, Rodney Brooks stood down from his role as the boss to test his robot-building mettle once again. The challenge? To build the world's first truly affordable, socially interactive robot.
Operational?
When we were asked for this proposal, there was 9 months to do it. And now it looks like we're going to get turned on around this week, which leaves us 5 months and a week from start to finish to get this whole thing working.
That's why I'm running for the hills.
They'll need to pursue every shortcut they can.
Notice this floppiness here? Is there a way to tie that down?
Are you opposed to glue?
I'm not opposed to glue, so yeah, because I want them fixed. You know?
The challenge the Pentagon has set is daunting. The robot has to be cheap and built from scratch. And in 5 months, it has to be able to play an ancient Chinese board game known as Go.
Tough, really tough.
The game of Go requires subtle human-like touch and dexterity. Characteristics yet to be conquered by any robot anywhere.
The hardest part about getting a robot to play Go is really the manipulation. Picking up the piece without knocking the pieces next to it. That's a very delicate task.
And motor skills are only part of the Play Go robot's problems.
Here's a Go set.
Its hardest challenge is to see and understand its human opponent's every move.
It has to be able to interact with a person because it's playing against a person. So it has to be aware of the person, be aware of what the person is doing, and then take turns and do appropriate things in a social setting. It's got to be flexible.
If Professor Brooks can piece together an affordable machine with this degree of social awareness and dexterity, there are far-reaching applications for military robots. And for Professor Brooks himself, lucrative possibilities in the marketplace.
If we can succeed with this robot, I think we'll be almost to the point to be able to build prototypes that could actually work in factories and be flexible assistants to human factory workers. This, I think, will lead to yet another revolution in the way we do work in the world.
But if Rodney's robot revolution is ever to materialize, there's another major hurdle these robots must overcome. Robots come with lots of bad PR.
Robots and conflict are a Hollywood staple, but I always like to point out to people that Hollywood isn't entirely accurate, because if it was, there'd be ghosts everywhere and we'd be fighting aliens. But that doesn't mean that that's what's really going to happen. We are in control of making the robots.
Professor Brooks wants the Play-Go robot to be accepted by humans. Fortunately, he won't have to start at square one. Domo is the world's most sociable robot. Under Brooks' mentorship, it's taken artist turned MIT roboticist Aaron Edsinger 7 years to create.
So currently, what Domo is sort of there for is to do research into manipulation, how to use your hands, how to, get a robot to use its hands, and to do jobs that are useful in human environments. So having a robot in the home helping a person, say in elder care. So that's sort of the space that we're working in for Domo. So right now I've turned on some Domo's basic visual system. So right now it's making eye contact. Domo will be looking around, and when it detects you, it'll direct its eye gaze and make eye contact and hold that for a little bit. And it really is sort of a powerful moment. I think we're just built to enjoy eye contact, read a lot about someone's personality and so forth from that.
Domo's eyes make it easy for us to relate to it. That's because a person intuitively knows when Domo is focusing on them and ready for action. Social anthropologist Kathleen Richardson has studied the way humans relate to robots.
From my conversations with roboticists, they're very conscious of the public perception of robots. How robots, we imagine the robot as the Terminator creature, hell-bent on destroying us. And, that's quite a challenge for roboticists. So they've developed various strategies to put us at ease with machines. And one very specific way that they do that is make them look cute and friendly. So you put the human at ease when they're interacting with them.
It detects that somebody's there.
It's so cool.
So you can try.
Okay.
So you have to say Domo here.
Domo here. Wow. That's so cool.
It comes back to the idea that if a robot behaves in a way that's familiar and human-like, then you can automatically default to some kind of intuitive, spontaneous interaction with them. So therefore, regardless of why the robot might be behaving in that certain way, you put a face on a machine, you think you've got a friend.
But Domo is more than a friendly face. It has the ability to reach out and gently touch a human.
It's got a hold of my hand. It's actually sensing the force. It's not in any danger of crushing my hand. So it's got a fairly soft grip. But it's also responding to the forces that I place on the arm. And this is actually what makes Domo fairly unique, is that it can feel that.
It's this sort of inbuilt awareness which will be crucial for robots to safely enter human society. The pre-programmed actions of today's industrial robots make them an altogether more dangerous beast. Unlike Domo.
Ouch.
It's just said ouch. It's feeling too much force in the arm. It doesn't like this. There we go. So this type of, human-robot interaction, communication is actually really going to be key when you have robots working together with people in the home.
While Domo has been a success, its design has been expensive and painfully slow. And now time is a luxury Professor Brooks just doesn't have. He has to build the Play-Go robot in under 5 months for its debut at an annual Pentagon presentation. What's making matters worse for the professor is that others are now hot on his heels. Google, Microsoft, Sony, and Honda are just a few of the companies racing to create smart machines that will change everything.
An increasing amount of companies believe that the actual time is now for this market to take off. Bill Gates himself said this market will take off in the next 5 to 10 years. So for the personal robotics market, we're forecasting it to be a $15 billion market by the year 2015, which is pretty large considering today it's more like in the tens of millions of dollars.
Those investors are willing to bet their money that robots will soon be embraced by households and businesses.
Lars, ROBOTICS.
And Professor Brooks hopes that making his new Play-Go robot affordable is the first step in robots becoming an essential part of every home.
When I was born, there were maybe a dozen or 20 computers in the world. Now there's more computers than there are people. I think the same sort of thing can happen from robots. Robots will make our lives better, and maybe, before I pass on, we'll have more robots in the world than there are humans.
So in the future house, the humanoid robots will be picking up objects off the floor and putting them away for you, hanging up your clothes, folding your laundry, things like that. It's going to take a long time to be very, very affordable for the average person, but over time you'll see robots will become increasingly complex and more people will be willing to spend more money on them. In fact, in some point in the very far future, I expect that many people will pay almost as much as they do for their car on a robot.
Car manufacturer Honda has built Asimo, a humanoid robot perceived by its many fans as the pinnacle of robot design. But it's taken Honda 22 years of research and tens of millions of dollars to get Asimo to walk and even run.
You see it do some things in a natural way and you can assume it does everything, but it can do a tremendous amount. These are quantum leaps in terms of mechatronic packaging, in terms of just the ability to walk and to run, and a robot of this mass and size to be able to achieve these things, in some cases on uneven terrain, is remarkable. But is it ready for going into your house? No.
With Asimo, looks can be deceiving. Very few know that its movements are largely controlled by a human. It's not independently reacting to its environment. And if there's any unanticipated change to its program, it malfunctions. And Asimo is not socially aware. Its companions are responding to it rather than the other way around.
There are some mechanically sophisticated robots around which are really remote-controlled toys, but unfortunately they've been presented as though they're autonomous, when they're not autonomous. And it's really saddened me when even science museums have put them on display and kids have thought that this is what robots can do, when they can't.
When it comes to genuine robot autonomy, there are many steps on the path to true independence. The first baby step is remote control, where humans govern the robot with a handheld device. The next step is teleoperation, currently used in what looks like space-age surgery. Doctors at the University Hospital in Strasbourg, France, are mastering the most pioneering surgical robot ever invented. It's not an autonomous robot. Its tiny fingers are controlled by a human. but it makes further independent adjustments of its own to improve the surgeon's performance.
There are so many possibilities that, for example, we put two robots together facing each other with two surgeons sitting down at a console so as to be able to work in a very small operating field with two surgeons, which you cannot do with microscopes and surgical hands because they're too big. So there are a lot of things that are being developed, and yes, the sky's the limit. It's very exciting.
But for robot scientists, true robot autonomy, a machine capable of perceiving the world, capable of making its own decisions and responding to humans, is the holy grail. And for many, the biggest challenge is to package all these qualities in the humanoid form. Back in Boston, robot scientist and commentator Daniel Wilson is well aware of the difficulties ahead.
A humanoid robot is a particularly hard robot to build because it incorporates so many different problems that have to be solved before the humanoid will work. So it has to figure out where it is at, where other people are at. And then there's speech recognition, emotion recognition, gesture recognition. And so all of this has to be built into one package. And any single one of those tasks is a PhD thesis. And so if scientists want to build the whole frickin' enchilada, then they have to solve all these problems at once.
At the Artificial Intelligence Lab at MIT, Rodney Brooks' team has only 4 months left to produce the Play-Go robot. Should they succeed, Play-Go will underpin the next phase in producing robots with greater autonomy. Rodney's starting point is to write a software program so the Play-Go robot can actually see.
So it has to be aware of the other person and when they're moving. It has to be aware of its hand and what's in its hand. It has to be aware of where the bowls are with the stones in. And it has to be able to look at the board and see where all the pieces are. So to find the pattern of stones on the Go board, we're taking the image that the camera sees when the head comes down and looks down at the board. And what I'm working on today is writing the code which will let it look at a board and see where the pieces are so that it can then feed that to the Go playing program to tell it where to make its next move.
To be able to see, the Play-Go robot must deal with a whole range of problems. Depth of field, texture, varying light conditions. The sort of stuff that humans do without thinking.
Basically what happens is human beings think that the things that are hard for us are the hardest problems to solve, when in reality, all the things that seem really easy to us are easy because we have so much built-in machinery that's evolved over millions of years in order to solve those problems. So those are really the hardest problems of all.
Rolo, answer the door.
And since humans have the benefit of millions of years of evolution, how realistic is it to build a sophisticated robot in under 5 months? At MIT, they're 1 month in, and the Play-Go robot is taking shape. Every structural element has been handmade by the team, like this neck piece. It's up to Professor Brooks to make sure everything is fitting into place. As team leader, he needs to stick his own neck out beyond what is considered possible. And especially to consider how a machine perceives the world.
Sometimes I try to imagine what it is like to be a robot, and I think it's probably some sort of drug-induced stupor where things sort of appear and then disappear, and it doesn't really know what's going on in the world, but it sort of gets little glimpses of things that make sense, and then they fade away. And so over the last few years, I've been thinking about how to improve robot kind.
Robots have come a long way in the time that Professor Brooks has been building them. In 1977, he was at Stanford University as a young researcher working on a robot known as the cart.
A very simple robot, but it used vision. And I ended up running around getting things set up for a run. And a run would happen at around midnight when other people weren't using the main computer, and would last for 6 hours. And on a good night, the robot would go 20 meters in those 6 hours, perceiving the world and avoiding obstacles. It would stop and then compute for 15 minutes and then decide to move about a meter. It was a bit frustrating, actually.
In the past, robots like the cart were so slow because every movement required a three-stage process. It first had to see the world around it, then make a 3D map showing how best to avoid any obstacles, and finally tell its wheels to move. For 23-year-old Brooks, things needed to move a lot faster than this.
It wasn't too long after that I started thinking about, well, insects don't have very big brains, but they can sort of fly around and avoid stuff quickly. So what was going on? Something was organized different in the way these things were operating.
Suddenly, Brooks had the answer. Ants. He saw that ants on rough terrain frequently miss their footing and stumble before moving forward. Obstacles were no big deal. The key then was to get the robot to physically sense its environment and respond to what it encountered.
I thought, why not connect the sensing directly to the action and avoid the planning? And that was my big eureka moment, which changed the way I thought about how to build robots.
In the summer of 1988, Brooks produced an insect-like robot, a six-legged artificial creature known as Genghis.
We made the robot sense forces on its legs, and if a leg was lifted up, it would swing it forward and then down. So now to make it walk, all we had to do was sort of metaphorically tickle the legs one at a time, and then as a leg swung forward, it would push all the other legs back just a little bit, and that made it walk. There didn't have to be a central controller. It was all distributed little processes in each of the legs communicating with each other. And we did the whole thing start to finish in 12 weeks. It was the best 12 weeks of my life.
3 main engines up and burning. 2, 1, and lift off.
Professor Brooks' eureka moment revolutionized the world of robot design and now forms the basis of millions of robots, like the Mars Explorer robots, to swarm robots, and robots on the battlefield. Rodney's breakthrough also led to a whole new field of robot design, known as biomimetics.
These are robots that are inspired by the principles that are incorporated in living animals. So the robot comes off the assembly line already with a lot of intelligence just built into its structure.
Brooks himself was not slow in taking up the opportunities that Genghis presented. In 1990, he established his company, iRobot, which produces a range of behavior-based machines, including robots for our homes.
I don't know about you, but I live with a bunch of animals. My kids are pigs, and my husband is, as soon as I clean the house, it gets dirty again. That's why I have an iRobot Roomba.
Overnight, the Roomba became the new man's best friend, and iRobot became a darling of the New York Stock Exchange. It's now worth over $300 million, and Brooks is a founding shareholder.
I think scientists want to uncover the truth, what makes things happen in the universe. I think engineers, and I'm an engineer, want to build things that do stuff in the world. And you can do stuff just as an art form, or you can do stuff that makes a real impact on the world. And I'm sort of after making a real impact on the world.
Now Rodney's reputation has a lot riding on making a breakthrough with the Play-Go robot. Can he reignite the genius of his youth?
We've had the body for a while, but now we've just added the arm. And so we've got a shoulder back there, an elbow here. This wrist goes up and down, and we'll be putting the hand on here in the next day or two. Now, I've only just got this together for the first time, and in these joints there are spring elements here, which means it's not rigid, which means the control system is a bit tricky. As we're starting it up right now, we don't quite know exactly what's going to happen, and it's still a bit shaky and flaky. Okay, you ready?
I'm ready.
Be ready to switch off.
That was tough. Ouch.
I don't seem to have any longer power.
Well, that didn't quite work.
Ouch. Ouch.
That was fun.
Ouch. Ouch.
You okay?
Stop shoving.
We've got about, 9 or 10 weeks till we're supposed to show this working. And as with all things in development projects, research projects like this, things always go much slower than I expect, much slower than I think we can do. We're such optimists, you know, we think that everything's just going to come together smoothly. So we designed the arm, and yeah, we've got that figured out. But then when we put it on the body, things weren't as smooth. So it's going to be interesting to see where we are 10 weeks from now.
Despite the recent setback, Rodney, the eternal optimist, is already looking for potential customers for his new breed of robots. Here in Massachusetts, electronics giant Jabil wants to keep manufacturing in the US. To do so, it needs to keep labor costs down.
So for us, when there's a lot of hand assembly, something that we can't typically automate with machinery that you'll see out on the floor, we would send that to a low-cost region because the labor's cheaper, they don't need the machinery. So you're going to come up with a solution that even
increases the productivity of American workers so you can do it in-house.
Instead of moving it low-cost, where lots of hand people are doing it, instead we could automate it and keep it here. Great.
Rodney and his team go behind the scenes, observing what capabilities they must put into Play-Go if they're to get ahead in the robot race.
So what he just pulled that, I just want to point out to everybody, he pulled that out, lifted that out of the thing, and then put it over on the tray. Thanks. Now, in a Chinese factory where low-cost consumer goods are made, people are sitting on either side of a conveyor belt, and parts coming, they're not particularly oriented the same way. They pick them up, they do some operation on them, they put it down, and some of them, the operations are pretty straightforward. But when we get to something like this with this floppy cable, that's really pretty tricky. Dealing with this very floppy thing, I think that's going to be a real challenge for our robots.
Jabil says in order to stop jobs being sent offshore, it's willing to consider robots to work alongside humans. But could this be the beginning of a shift to replace humans with a smarter breed of robots?
The cost of labor is going up in different countries, and as each country starts to develop further, the cost of labor goes up, and people can move their manufacturing processes from one country to another, but eventually I think we will run out of countries. So eventually, at some point, I think we will have a need for more machines and more robotics to replace human labor that is becoming too costly. There's no salary for the robot.
The Play-Go robot's hands are being developed separately from its body. Its extra sensitive fingertips are inspired directly by the finger pads on a human hand. It has 8 touch sensors inside each finger, enabling it to select a slippery stone and place it directly on the board.
If we can succeed in getting this robot to do all the mechanistic things of playing Go, I think we will have gotten a lot of the capabilities that we need for a robot that can be a real helper to an ordinary factory worker.
But this is not just about business. It's about massive social change. Throughout the developed world, the proportion of older dependent adults is increasing, putting pressure on the young to be yet more productive. In Japan, the birth rate has plummeted and older people are living longer than ever before. By 2050, almost half the population will be over retirement age. there won't be enough people to care for the elderly. Some Japanese scientists think they'll solve this problem with robot companions. This is a humanoid robot known as CB². It's the brainchild of Professor Minoru Asada.
Hi!
Professor Asada.
Hi, how are you?
Good to see you.
Hi, good to see you. Long time no see.
Yeah, I think it was at Tokyo University.
Yeah.
Professor Brooks is here to see how Japanese roboticists are designing machines to work as human helpers, just like the breed he has in mind.
My idea is that the humanoid, it's kind of the ultimate goal. You know, if you try to design the humanoid, you have to know everything.
In the US, the robots that are getting deployed are very task-oriented. And that, in contrast, in Japan, the research often seems to be about robots that might be companions for the elderly.
Sure. That's a very serious issue in Japan, because people are getting older and older, and the older people expect to be supported by their family member or their relative and so on, but sometimes not. Therefore, there's a big potential the market of the to assist to help the senior people.
Okay. Something's happening.
The Japanese government has poured millions of dollars into this robot's development.
So you can touch, right?
Yeah.
Okay, and then it has 200 tactile sensors.
The CB² is soft and powered by compressed air. Unlike its metal and electric counterparts, CB² is meant to be handled.
He doesn't look very happy.
Okay.
In order to help the elderly, a robot will need to be able to respond instantly to a human's weight and balance.
So, you know, as I pulled, I could really feel it trying to do the thing. So it was responding to what it felt from me. It wasn't. I think if you just look at it from outside, it looks like the human's doing all the work, but the robot's doing a lot of the work in response to the human.
Yes, that's very, very important issue. In future, we make the robot try to estimate the predict the human motions. So in future, we expect the robot to assist senior people.
But the idea of robots helping us when we're old makes some people very uncomfortable, like robot ethicist Ron Arkin.
I wouldn't say it's solving a problem, I would say it's avoiding a problem. Part of the issue is what is the appropriate use of technology from an ethical perspective as well. And is it okay if we abrogate our responsibilities to robots to take care of our elderly and give it up? What if you put your grandfather into a home and you were supposed to go visit him on Sunday, but you were busy, didn't feel like it, and you said, don't worry about it, the robot will take care of it, he'll have a good interaction today.
But there's a reason older people in Japan are more accepting of robots as carers.
Fortunately, somehow Japanese people are very, very, friendly with robots because, a kind of animism or something. The people think that everything has a soul. So of the book, so of the table, and something. Therefore, robot, should have a kind of soul we can share.
And while animism, the belief that everything has a soul, makes companion robots easier to accept in Japan, there is another factor.
Soaring high in the skies, he may be small but only in size. Astro Boy, he is...
Astro Boy is a tremendously popular Japanese superhero from the 1950s. A little child robot with superpowers he only uses for good.
There's Astro Boy, which is like the Mickey Mouse of Japan, and he's always saving people's lives and doing really great things. Whereas in the United States, the robots are usually malfunctioning or they're usually trying to kill somebody. So it's a pretty distinct difference that you see there. I think to some extent in the United States we do fear the technology, and we don't necessarily see it as a solution to a problem.
You have done a splendid job, Astro.
Thank you, Dr. Elephant. Thank you, Chief.
やはりコマーシャルなんか出てきてるロボットでもね、やはり見かけのいいのがやはり可愛いな、いいなと思ってしますね。
可愛らしいのがいいわね。機械でな、こんなんかってやるようになるんでしょ。
For a robot to be able to play gate ball or to have any ability to help the elderly, it has to possess a high level of intelligence. Central to CB²'s design is the idea of learned intelligence.
Which one? Which one? All these old people around me are trying to get my attention.
CB² is a machine which learns from its environment and is meant to be touched and talked to. It's basically an oversized robot baby. Underlying the robot's design is one of Rodney's main theories, that infant learning is the key to understanding intelligence, and infants learn through their senses, through their bodies.
We hypothesize that having the body is essential to growing intelligence. So we're exploring that with robots. Can we build robots that maybe have more common sense about the world, the ones that have been programmed to be purely intellectually thinking about the world without experiencing it?
Hello, Kismet. You gonna talk to me?
In 1997, Professor Brooks and his team built Kismet, a small robot with eyes, ears, and a mouth so it could see, hear, and experience the world around it.
Look at my smile. Oh, that was cute.
Chief designer Cynthia Brazil observed that a baby learns by paying close attention to its parents.
Hello, Kismet.
You know, as parents, when we exaggerate the prosody of her voice, you know, going, oh, good baby, you know, or our facial expressions and our gestures are so exaggerated, a lot of that makes it much simpler for the infant to actually understand those signals. And so for Kismet, that made it much easier to perceive these cues and interpret these cues.
Good job, Kismet. Very good, Kismet.
The team emulated the way in which parents use vocal emphasis to teach their babies.
No, you are. Go. Go? No, I'm not gonna go. Oh, yeah. You're so silly.
Through this unique approach, the team created a robot that is able to produce moment-to-moment and seemingly natural human responses. This enables Kismet to appear to have social intelligence.
Social intelligence was something that, you know, robotics people just didn't think a lot about, you know. We take it for granted. It's like we just interact with one another. We just understand in a conversation what you mean. It's obvious to me, you know, and what we're finding, of course, is it's also really hard to build a machine that can really understand people as people.
No. That's not appropriate. No.
Perhaps it's not the robot understanding us, but it's us watching and understanding Kismet.
I've interacted with a sociable robot, and I think their success is because of what we attribute to them, rather than what they do themselves. And what we attribute to them is not a technological question, it's a sociological and anthropological one. All the scientists had done is allowed it to do a random sequence of behaviors. However, it was me who attributed all those thoughts and feelings and activities to it, and all those intentions. And I think that's often the success of this technology, is what we're actually putting into it.
I'm not quite sure.
I love you.
Aw, did he say he loves me? I love you too.
Humans are just suckers for anything that looks human. We will anthropomorphize any sort of object that's out there. It can be a car, it can be whatever. We will start calling it by a name, and we will look for faces and wherever we can find them. And so I think robots just take advantage of that directly. And they don't even have to go very far in order to do that. It can just be a couple of eyes and a mouth, and that's it.
Like Kismet, the Play-Go robot is expected to have a degree of lifelike behavior. With such little time left, a lifelike face is not a priority.
Tilt it down to look at you. This is the first time I've got all the software in together, so let's see if this works.
Ouch. Stop shoving.
Is it balanced yet?
No, it's not balanced. It's not. So this
So
is.
you're feeling confident about that other bug?
This is a little risky.
So I think I'm all...
Let's figure out which one's which. At the moment, I can't figure out which camera's which automatically, so I'm just gonna... Can you put your hand under the hand camera? Oh, okay, that's in the right place, thanks. Can you put your hand up in front of the left eye? Okay, so let's see if this works, Anne.
Professor Brooks hopes the Play-Go robot will soon begin to interact socially. To do this, the robot has 4 cameras to see the world and special person detection software. When it's all up and running, it should recognize when a competitor is at the board, ready to play. But there could be a hitch. Neither Rodney nor Anne know how to play the game.
It's a good thing we don't know how to play Go, because this probably looks really silly.
The robot doesn't know how to play either. So the team will download software containing the rules of the game, much like a computer can be programmed to play chess. The Play-Go robot will consult the Brains Trust before it makes a move. It's a tentative step towards becoming an independent player.
The Play-Go robot is independent in that it doesn't need to be told to play Go. It just sees the Go board in front of it and it knows what it should be doing. As we get more and more robots in our lives, we need them to be operating independently so that we don't have the cognitive load of figuring out what to tell them to do at every single instant of time. They have to be doing it themselves.
Of course, the US military does not ultimately want a robot that can play board games. They're after machines that will go where humans should fear to tread.
We're going to see a transformation in the US military over the next few years. There's been a congressional mandate that there should be less manned missions, more unmanned missions on the ground. And so we're going to see the infantry starting to have robots in each group of soldiers as forward scouts.
The US Congress has allocated $165 billion to deploy military robot systems over the next 15 years. Semi-autonomous robots, like unmanned aerial vehicles, need human assistance to take off and land. But all other actions can be pre-programmed by a computer, and then the robot is on its own.
You can mostly just watch the screen, you can stop it, hover and stare.
Robot ethics.
The robot doesn't have to come up with the ethics. There are people in the machine ethics community that are actually concerned with how an intelligent system, a robot or otherwise, would develop its own sense of ethics. But the last thing you want in the battlefield is a soldier to develop his own sense of ethics. You want to tell him what is ethical and what is unethical, and this is what is permissible, and this is what is not permissible under law. And it dawned on me that if we as soldiers are required to adhere to these traditions and laws, then why not our robots as well?
Ethicists, it seems, are finally catching up to where science fiction guru Isaac Asimov was in 1942.
Asimov is famous for his 3 laws of robotics, which talk about a robot causing no harm to a person, maintaining itself, etc. Currently, we can't program the 3 laws into our robots because our robots can't perceive the world well enough to understand when the laws would be applicable. I think as our robots get more sophisticated, we are going to want more and more Asimov-type laws programmed into them.
Some of the things roboticists are doing are creating a system of rules, but I don't think it'll be fail-proof. So even though robots may be programmed to not harm somebody else, certain governments and militaries may demand that that rule be removed.
The official launch of the Play-Go robot is close at hand. and the team has just begun a final series of tests on what's become a more simplified version.
We've got 2 more days before we were due to have the launch event, and I think we can get there, but we had to give up some stuff. We gave up the social interaction. We just decided we didn't have time to put that in, but we've got the essentials.
After 5 months of hard slog, the team has conquered the fundamentals. The Play-Go robot now has object recognition and touch sensors delicate enough to select a single stone from a crowded bowl. But the question is, can the robot integrate these tasks and play the game?
I am a robot that can play Go.
Anne, would you like to play a piece?
I'd love to play Go.
Let's see what happens.
I seem to be playing black. I am going to pick up a black stone.
No.
Yay. My move is E6.
E6. Wow.
Oh.
E6. Okay. E6. Well, I still got to find E6. And E's from the bottom. So now it's...
And then, just when it's all going so well, the Play-Go robot gets confused. Its ability to decipher the information feeding in from 4 different cameras overloads the system.
It's got lost. Yes. Okay, let me think.
Going on a journey.
Let me think.
Everyone crosses their fingers and hopes the Play-Go robot can clear its head and get it together to continue the game.
Okay, I'm going to set it going again.
I am going to pick up a black stone.
The robot makes another try, but this time is unable to pick up a single stone.
As with all academic projects, we've finally got just about all the pieces. We cut away the pieces we thought we could live without, and it's the last minute, and we're trying to integrate everything. And when we integrate everything, the units go wrong, this talks to that the wrong way. I've been battling with sign changes all day. No, I didn't get one.
One of the major problems that confronts robotics today is that of reliability engineering. How do we make this platform work 24/7 or be as reliable as your automobiles? This is a hard problem.
Come on.
It is a big ask to make machines that mimic day in, day out the complex skills that humans do easily. Progress can still only be achieved through tiny, incremental steps.
I am going to pick up a black stone.
Despite Play-Go's failure, today significant progress has been made.
The reality is we've actually figured out about manipulation, how to do it better. And that's what we were setting up to do. So, in a sense, we've done the science. It's just the dressing around it, the integration, which is really engineering, is what remains to be done to build better and better machines.
The Play-Go robot never did play Go at the annual Pentagon presentation. It was not to be the triumph Rodney Brooks had been banking on. But Rodney's Play-Go robot may be recognized for what it is: an important evolutionary step up the robot ladder.
Now we're focused on teaching the robots to do with metal what we do with our flesh. But as we do it, we're bringing the robots closer to us.
Whatever we create, whatever robots they are, they're not going to be very far from us in one way or another. They might not be reassembled in exactly the same ways, but they'll be very intimately connected with who we are as human beings.
People often completely underestimate how it's going to transform their lives. Many people have seen Hollywood movies and think robots are going to be able to do all sorts of wonderful things in the short term. But in the longer term, I think they really don't get how it's going to transform humanity as we go out hundreds of years.
You can't steal Daddy's cars! Whose cars? Please! Please!